So last time around, we were going through power consumption models, and kind of the goal was that could we develop some sort of an abstract model by which we can characterize at least digital systems, and we'll do the same exercise for other parts of computing systems, and later in the course for buildings and all. So what I had presented towards the very end was that very crudely we can think at a very high level that our systems have a few different components which correspond to the first term corresponds to kind of this power which is associated with the actual computation. So this is really when we do computation, then essentially we are turning gates on, off, we are moving charges through the gates, so capacitance is charge, discharge, and all of that takes energy because we are basically charging, discharging capacitances through transistors which have resistance. So if you kind of go back to your kind of physics from high school days, it's basically kind of, you can think of it as I have a RC circuit, resistance, capacitance, and current is flowing through it. So high order bit, but the main point for us to remember out here is that it depends upon frequency. So faster I do the computation, the more power I am going to consume. It also depends upon capacitance, and you can think of it as kind of a lumped capacitance corresponding to my whole system at a crude level. Really what's happening is they're kind of scattered all over at different points in your hardware. Alpha represents the probability at which it's switching. So like if I'm not doing any computation, then the different variables in my circuit are going to hold their value, and then essentially there is no charge movement happening. And then the interesting term is V square, the voltage square, and that arises from the fact that if I swing if the voltage swings are higher, then I need to move more charge around, and therefore more power gets consumed. So this kind of begins to suggest things. I can slow down F, but if I slow down F, then I will also do computation at a slower rate, so it may be not necessarily a win. As I slow down F, then I can also reduce the voltage because my circuit needs to run at a lower voltage. So, but this is a core computation term, but that's not the only term. The other terms are also very interesting. So this second term again happens when the clock switches, and that's because for a brief moment of time there is current which flows from power supply to the ground, and because essentially the gates, you can think of them as being short circuited for a tiny duration. This is usually small, but the third term is interesting, and that's the leakage thing. So the mere act of my system being powered up, even if it is not doing anything, even if the clock is not running, basically every little diode in my entire system is going to have some leakage current happening, little tiny amount of current, but added over hundreds of millions or billions of transistors, and that can become significant. More importantly, this term has been growing up as a ratio relative to the first term. So it used to be like, if you go back to 15-20 years ago, the first term would have been maybe 80-90% of the overall budget, but nowadays leakage can be maybe half the budget there. So it's becoming very dominant. And then finally you have this P leak, which refers to all the unnecessary stuff that we have, just a second, all the unnecessary stuff that we have in our system, which is just there as a baseline thing, right? I mean, so for example, if you think of let's say a laptop, there is power supply, all this kind of stuff, which is just the baseline power consumption is happening, some useless LEDs or things like that, these architectural components which are kind of just out there. So that's kind of that final bit. Okay, so I'll get to your question now.
So is P leak actually growing, or is it that all the other terms are shrinking?
So all the terms, the first term has been shrinking. That's one of the benefits. If you do scaling properly, certainly the first term scales down. When it comes to leak, it is growing in the following sense, that as we have been scaling down the technology, we have also been reducing the voltage. So if you again go back to, let's say, 80s and 90s, your voltages used to be 5 volt or 3 volt. Nowadays they are a volt, and they're much closer to the threshold voltage those of your E's, and that, so as your voltage comes closer to the threshold voltage, the leak part goes up. The other thing is that since things are running hotter, leakage increases under that condition. So leakage is going up, but more importantly, as a fraction, it has gone up quite significantly from being essentially negligible to quite significant. And the reason it matters is the following: that what this says is that even if I stop doing any computation, just a very common technique is something called clock gating. If I don't want to do anything, I stop the clock. Now that gets rid of these terms, so f equal to 0, but this stuff still stays there. And the only way to get rid of that is to shut the system down, power it off. But when you power something off, then restarting it is a very disruptive process. Your power supplies take time to come up, your clock has to restart, all the capacitances in the system have to charge up, so to say. So that process can be tens of milliseconds, or depending upon your operating system, seconds or minutes, depends on the scenario. So not very, so stopping a system and reawakening it is not as easily done. But on the other hand, if I was just focused on, let's say, the first term, then a very easy strategy is to make f equal to 0, essentially temporarily stop the clock. So this is called clock gating, where basically what we do is we have an AND gate sitting there, and then we basically make one of the input is a clock, the other is a control signal. We make it 0, clock stops going. So you do that, and you could do that at a very micro scale. I can look ahead that the instruction coming in next doesn't use floating point unit, so I can just clock gate the floating point unit away. I don't have to power it up and down. I just stop the thing. So that's effective for the first term, but not really for the leakage term. But there are other techniques for leakage that you can bring to play. We'll talk about it when we come to power management, but just to give you a peek ahead, in circuits, besides the power supply voltage, there is a second voltage which is called the so-called substrate voltage, which is essentially you connect a power signal to the silicon, the substrate on which the circuit is sitting. And by controlling that, it turns out that you can control that threshold voltage I referred to. And that in turn indirectly can control the leakage. So you have some games you can play. So in effect, our hardware gives us these knobs. And one way of thinking about it is that I can keep these knobs at different settings, and then I get different performance versus power characteristics. And so I can exercise some degree of control over these things, but they all come at a cost. I mean, besides how to manage that process, there is also the complexity of the underlying hardware that occurs. The other thing to remember is all of this thing is still about this nice digital CMOS kind of part of the system. Your analog circuits and non-electronic components, displays and things like power supplies and these kind of things, they are following some other power consumption thing, which kind of I lumped under this P leak for now, but they have their own kind of behaviors. Okay, for example, a few slides down, I'll talk about displays. So things like different kind of displays, what's the color palette, that makes a difference on the power consumption on display, refresh rate, that kind of things. And so there are a lot of other components which kind of also come into play. So keep things in perspective that this itself may be a small part of power consumption of the overall system. So as technology has scaled, a lot of these things that affect the specific numbers kind of change. One which I kind of just referred to is that the supply voltage that we use, or signal voltage, so like what voltage is 1, what voltage is 0 in our digital systems, that has been going down, as has the so-called threshold voltage. Again, this kind of stops at many years ago, 130 nanometer. We are kind of many generations from it. The point is that voltages have sort of gone down over the years. So what has been happening is that as we have lowered the power supply, which has been lowered partly because of these power considerations, partly because of some additional considerations having to do with reliability, then to maintain speed, we have lowered this key technology parameter threshold voltage, because the speed at which our circuits operate is decided by the difference between the two. But that headroom largely disappeared in the sense that you saw these two curves come about. This gap between the two curves is what dictates the speed to the first order, and as they have kind of converged, we lost that too. Back in 90s and early 2000s, we had this ability, we played this game, that's behind us. So we kind of plateaued on that front. When the net effect of this is that now we are operating very close to the so-called threshold voltage. Long story short, this has caused the leakage component to grow up, both in terms of absolute value and even more so as a percentage of the overall thing. So we basically at this stage are in a situation where whatever technology could help us in terms of power thing, that's behind us. In fact, it's been behind us for a few years now. So there's very little, you cannot simply say, the IC designers and all will solve the problem. They don't. So brings to be, brings up the need for managing things more properly. So what happens is this static power component, the one which is the leakage one, is called static. The other one, the F-dependent one, is called dynamic. So the static one is kind of a bit nasty in the following sense that even if I'm idle, I'm still burning it. Okay, so and as I just talked about, shutting things down can be, unless you really design the system, every part of the system very carefully, shutting things down has its own cost. So if you think of a system, I have several things I can do. I can slow it down. And the extreme case of slowing down would be I don't run it, but it's still powered up. And then the final thing is I can really power it down. And when it comes to powering it down, I can have different stages of powering it down. Maybe I power down the whole system, or maybe I power down parts of the system. Okay, so that they will have different cost of waking up. So what this thing is showing is the following: that if you think in terms of I have a system which has some time slots, and I have some task which arrives, and then I run it. So let's say during a particular time slot, I run the task for a while, the task finishes, and then I'm no longer doing any computation. Okay, so let's say at that stage, what I've done is I know I have nothing to do, so maybe I stop the clock or I gate the clock. So at that stage, I am in kind of an idle mode, and then again, I consume some energy performing the task. Next time slot, again I stop. That's how the dynamic component will behave like, right? Because I get the clock, so the dynamic component basically power goes to zero, so the energy is flat out here. But leakage one, because the system is on, this keeps growing. So this tension between these two, the dynamic part, which is dependent upon the load on the system, the work the system is doing, versus the static part, which is purely just because you are on, ready to do work. The ratio between the two becomes important. So if I have a system where leakage is very high, then essentially, if I have these long periods of idle time, then the energy that goes during that while I'm doing nothing becomes important. And that is the cause behind the Y offset, the zero offset on the Y curve, which we saw when we were talking about energy proportional computing. Because this term doesn't, here the power is not zero when I'm doing nothing. Okay, well, dynamic one power is zero when I'm doing nothing. So when you kind of add these things up, it turns out that there would be some sort of a optimal combination of power supply and voltage that would occur. So if you look at this dynamic energy, or what is termed out here as switching energy, that's one term, but then I have the leakage term. And if you look at the behavior of the leakage term, what's basically happening is that as the supply voltage goes up, or as the frequency goes down, then the contribution of leakage energy begins to head up. So the name of the so from a from what emerges from this model then is that when I'm running the system, I have to somehow kind of find the sweet spot in terms of these, and depending upon specific system characteristics. So last time I had asked this question, whether you should sprint or whether you should do marathon. The answer really depends upon the relative contributions of these terms. If I have a system which is where the leakage component is close to 0 or very tiny, then essentially I am working with going back out there, I'm playing with this term. This first term dominates alpha cv square f, and that opens up a nice set of possibilities. But very roughly, my strategy in that case would be to run just at the right speed. Okay, that is, I should occupy all the time available for me. So what that means is that when I'm looking at this plot out here, then essentially I want the slope while I'm active to be such that it just finishes a task by the time the allocated time is over. So it turns out that as long as your power versus voltage curve is a convex curve, like the v squared case that we have, that strategy works fine. That is, there is a single speed which is the optimum speed in that case. If on the other hand, leakage dominates, then my strategy would be run as quickly as possible and then shut the system down. Not simply idle it, but shut it down. And then I have to design the system so that it can wake up very rapidly. It can be shut down and woken up very rapidly. And that requires additional thought and all, including what is happening on the software side as well. And obviously, tiny amounts of shutdown may not be feasible because certain things in the system just take certain time, but you could do these like micro sleeps and all, like really begin to exploit those as well. So what all of this then leads to is, and this is old piece of work out of group at MIT, they had a tool called Joule Track which had built around this. So very roughly speaking, you can say that, look, I have a processor. I have really, for now, two knobs, voltage and frequency. So first thing to keep in mind is, if I have a particular frequency, and to sustain that frequency, you need certain minimum voltage, because we saw that voltage affects the speed. But any excessive voltage is basically going to waste power. So an assumption that we should go in with is that if I give you a speed, f, then there is a certain minimum voltage that you should work at, and no more, because anything more is basically pure wastage, because your speed is just dictated by f. If voltage is smaller than that minimum, then what do you think will happen? So my circuit is too slow. So if you recall from your digital logic classes, there's a critical path which you need to sustain a clock frequency. So if my voltage is too low, my transistors are not fast enough, so my critical path will be violated, and therefore the delays to my circuit, the computation in them will not finish in time for the next clock edge. So I will get errors. Okay, and it's not that, I mean, usually what happens is that it's not as if everything stops working. Your critical path will fail. So you'll start seeing noisy data or whatever, your program jumping to weird places and stuff like that. So the failure is a little bit gradual. But that's kind of the idea, that there is a certain, that for a given clock speed, you need a certain voltage. And people who go into like gamers and all, who do cool their machines and stuff like that, they do overclocking of the processor and all. They basically rely on the fact that when processors are made or other parts of the system are made, they are kind of very conservatively designed. So when Intel says that this thing is a 2.48 gigahertz processor, it doesn't mean that at 2.80001 it will fail. It's just that they basically decided that if you run it at 2.8, in all likelihood it will work fine. But in that mix, you may be lucky that your particular processor is actually capable of running at a faster speed. And also by cooling and all, you basically turn things to your advantage. So Now going out here, the goal is that I want to give you a program and I want to estimate how much energy it's going to take. So what we do is we basically, based upon the insight, we basically say that, look, I have voltage and frequency as two knobs. They are kind of dependent. That is, you should make sure your voltage is sufficiently high. Then you can basically say that there are really two terms that matter to us. There is that V square F term, all that alpha, C, stuff like that, you can think of it as a constant, some K1. And then there is this other term, which is the leakage term. And it turns out that leakage does have some voltage dependence, but no frequency dependence per se. So there is a second term. And here you see some exponentials and all. They come from the physics of the devices. But the main point is that this is not frequency dependent, other than the fact that I need to make sure my voltage is selected carefully. So now what we have out here is kind of this model out here where I have two constant parameters K1, K2, and I have frequency and voltage, the two knobs. Oh, sorry, there's a K3 also and the exponent. So these things. And from that, now I can basically say that, look, what would be the energy consumed by if I'm running a program with n instructions at runtime. And here we are making a simplifying assumption that all instructions are the same, and also it's not like add takes more than multiply or stuff like that. So, and to the first order for simple RISC processors, this is a very reasonable model. All instructions are the same, so all I can focus on is the count of the instruction. If you needed a more elaborate model, you can replace n by maybe different types of instructions, maybe integer arithmetic instructions. I have n1 of them, floating point I have n2 of them, and the rest I have n3 of them. So I can divide them into buckets. So you can complicate the model a little bit. But what it boils down to is that will have the power component times n over f. So n is the number of instructions needed by the program for whatever, one iteration, one cycle, or start to end. And f is the frequency, so n over f is the time taken. So this is just time. You multiply this thing out, so now you have a model for the energy taken by a program which used n instructions at runtime. And finally, for a given voltage, there is a maximum frequency I can work at, as I talked about a short while ago. And it turns out that, again, from the physics of a transistor, there is kind of a reasonable looking model out here. Long story short, there are just a very small number of parameters out here. Okay, I've taken this complicated processor and reduce it down to this first order model, and then again with certain sort of simplifying assumptions. Okay, I have to make sure that the frequency, that my choice of V and F is such that F max is greater than whatever F I'm operating on. Okay, so I have to kind of make sure. What that leads to is so what we can do with this thing is we can fit this model. So it turns out, and that's the tool I was referring to. It used to be on MIT's website. This is, I'm talking about around 2000, early 2000 kind of time frame. So basically on that tool you could upload a program, it would run, profile it, get the value of n. Separately they had fitted model to a bunch of different processors, and then they would do an estimation. Point was that even this very simple model did pretty well on embedded processors, like these kind of these simple ARM processors. On the very right hand side you would see the percentage errors that they were observing against the real measurement. So as you can see, they are as good as they get. I mean, anytime you are in the single digit percentage error rate, I mean, it's probably lower error margin than everything else in the system anyway. So what this thing did in effect is treated the whole processor, all this complexity and all, in this very simple lumped single capacitance kind of model. With this model, you can begin to get a lot of insights around kind of things you can play your games. But very broadly, there are two ways you can exploit the knobs that you have, voltage and frequency. One is what is called as DVFS, dynamic voltage frequency scaling. A lot of work in 90s and 2000s. Now for the past 10 years or so, it's in commercial thing. I mean, you find them in your mobile phones, and on modern processors, particularly mobile processors, have these things. So the idea out here is in DVFS, you set V so that the corresponding F max is F. Okay, so kind of the idea is I would decide to run the system at a particular frequency, because maybe depending upon the workload and all. And then I will choose a voltage such that the maximum possible frequency for that voltage is exactly equal to the F I want. Anything more is wastage, anything less leads to error. So this is DVFS, and as you might imagine, this notion of I need to set a voltage which is corresponding with whose F max corresponds to F is actually tricky. How do I know what voltage will lead to an F max, which is right? So there is a bit of circuit magic that kind of needs to be done. You have to make sure that your estimates are robust across processors, over time, across temperature conditions and stuff like that. So this is great. This works very nicely. The only thing to remember is that its efficacy depends upon how large is the first term, the switching term, the dynamic power term. If that dynamic power term is very tiny, then this thing is actually not going to help, okay? Because your better strategy would be run at highest possible frequency that the processor can sustain. Highest possible frequency, highest possible voltage, and run as rapidly as you can, finish, and then shut the processor down. Case 2 is what is called as DFS, dynamic frequency scaling. And this is essentially, if you care about the energy consumed, this is essentially a useless technique. So in this case, what happens is we fix the voltage. The voltage is fixed. And then all we do is we change the frequency between whatever the lowest possible value through F max. Okay, so here essentially my system is always set to run at the highest possible voltage, or perhaps the motherboard is designed to be at a fixed voltage, and I just change this frequency. Why I said this is useless? Why do you think it's useless? Useless for the case when dynamic voltage dominates. So it's saving energy. If I lower, let's say my workload is less. So I lower, so I say, you had given me 10 seconds. If I run it at the highest possible clock rate, I'll finish it in 5 seconds. So I say, hey, I'm going to lower the power of the CPU by running at half the frequency. So I now use up all the 10 seconds, but my voltage is still set to be the same. Okay, so the V squared term is still the same. What do you think will happen to energy? Energy is integral P times P dt, right? So if P goes by half, if F goes down by half, then I'll need twice the time, right? So the area under the curve will remain constant. Okay, so this technique is kind of useless. This is what first came out in the market. The point is, it's useless. And in fact, if you have the ability to shut the system down, power it off, then it's actually worse. You should actually run as fast as possible and shut the thing down, as opposed to letting it run at this low frequency. So let's say you had a computer and you had to do a task which will take long time, some machine learning task, but you want to care about the electricity consumption. So you have two choices: let that deep learning run on your data set for a week at the slowest frequency, or run it for 3.5 days at twice the frequency. Former is going to be better, okay, and then you shut the system down because the area under the curve is the same. So without changing voltage also, you do not really get any gains. So the takeaway out here that I really want to sort of leave with out here is that very simple power models work nice. More recent work, as in over the past 10 years or so, let's say, have started going into other directions, like, this is a model for the whole processor. Could I begin to talk about subsystems of the processor? Could I begin to talk about how much each program was taking? Could I, so that I can then optimize things, okay? So I can find bottlenecks and all. Now, when it comes to measuring power consumption, One answer is this: I put current sensors and voltage sensors everywhere and do a real-time data collection. Problem is that while it works for experimental systems, it's not something that you can deploy because these things cost. But for experimental systems, there's a lot of work that people do. Like, for example, we take motherboards and whatnot and we instrument them. Professor Kaiser's group, for example, for a long while had these things where they had these Intel boards where every DRAM slot they had created a riser with a current sensor, and so they basically just heavily instrumented them so that at runtime the software can know what's happening currently. And there's similar things that sort of lot of other people have done. You can even buy these things, like for example, Qualcomm sells these evaluation version of their mobile devices which are instrumented with such sensors. So you can find out how much each processor core was consuming, how much was that going to cache. The problem that these systems face is firstly the cost of the sensors and all, but the other thing is very high amount of data needs to be extracted, and so your sensing itself begin to cost a lot of energy. But at the same time, the traction of saying that, I want to measure energy consumed from point A to point B in my code remains very seductive. So the other alternative is to use models like these. You basically, so this is one example, but you can imagine other types of parametric model. I take this parametric model, I run them on bunch of programs to find the best fit for the parameters, and then I use them at runtime. So I'll talk about it later in the course, but a lot of work of that nature on mobile phones. You would see that, so on Google, if you have an Android phone, you can kind of, at least for older version of Android, there are these apps available which kind of use a model of the phone, things like these, and then similar stuff for displays and all, and then use them for a runtime estimation. What you can find in these devices on mobile phones at least is the battery level, and from that you can do a whole device estimation. But for anything finer, you rely on models. So models are your friend, but models have to be aware of the underlying physics to some extent, and this is an example of a processor model which, as you can see, has a lot of the physical insights rolled into it. You could go even more detailed where you can begin to have transistor level models and stuff like that, but that we cannot sustain. The nice thing out here is with a very small number of parameters, half a dozen or so, we have a pretty reasonable estimate of what is going on. So continuing with our power consumption story, then what if you were to look at what kind of power consumption numbers and all at an overall system level that matter. So kind of some of the things that come apart is what happens when the system is off, what happens when the system is asleep, when it is idle, and so on and so forth. Some of the things that you would also see out here is that the effect that different choices can have. So for example, power supply efficiency, that's extremely important. Like if you look at, so this is for an iMac from 3-4 years ago. Power supply efficiency is 90%. Okay, so 10% is just going away in that little byte adapter that we have. In case of laptops and all, there's a lot of attention taken to display energy also. For mobile phones, for example, when they quote battery lifetime and all, from what I understand, typically Apple uses a 5% duty cycle estimate. That is only 5% of the day your display is on. Okay, so those kind of things. But the split, so one way of thinking about it is that a crude power model for your system or subsystem is in terms of these distinct modes. When it is idle, when it is shut down, when it is display is on, display is off, these kind of things. So you can think of your system as having these different modes, and then for each mode you can associate kind of a power number. And then some of these modes are more complicated because I can change voltage frequency, so then I may have many substates within there. So we'll see later on, but you can think of it as sort of a state graph, and your system transitions between them, and then for each state you can have a particular model that you can work with. Power consumption in servers, we had a look at it in the previous lecture, so it's the same slide, but one of the thing is when we go to servers, servers tend not to have any displays and all, so they are kind of meant for use in sort of server rooms and data centers and all. But it does, you would see that, for example, across different kind of things, blade versus rack servers and all, there are kind of distinctions that occur. Processor, as you can see, in this case, in a mainframe kind of setting, the processor is a tiny part and everything else accounts for a lot. One thing you would also see is that power subsystem, this is just a power supply, and the cooling system, they're actually a fairly significant part of the overall story. So something that you should not ignore as well. I'm going to skip these. People, there are tons of papers in academic conferences where what people do is they take some interesting device and they dive into its power consumption thing, and then they try to develop a model. In recent years, there has been stuff, and we'll see some of them on things like Google Glass or mobile phones and these kind of devices. In terms of project ideas, that could be an interesting direction to take, like doing a deep dive power analysis of some interesting new type of device, maybe a drone, maybe a VR headset, or these kind of things are possibilities also. Okay, I'm going to skip these and let's talk about power consumption in displays, because displays matter a lot, particularly, I mean, certainly even with laptops and obviously big screen TVs and all, but mobile devices, they play kind of a quite a significant role. So displays consume a fair bit of power. As I said, that battery life numbers are quoted at 5%. There are two very broad technologies. There is the LCD, which is a backlit technology. That's what, for example, my laptop has, or that's still the dominant technology in the laptops. Apple's devices, still Apple's iPhones, use LCD. And the other one is OLED. In OLED, so the difference is in LCD, my display consists of these liquid crystal, basically, which essentially affect the amount of light passing through it, and there is a light behind the display, and depending upon what's passing through, so the pixels themselves are essentially blocking or letting light go through, and you have some color filters and all to get the color effects. OLEDs, on the other hand, basically the pixels emit light, so these are emissive displays, and that's a more recent technology, and those gorgeous displays in Samsung's Galaxy devices, for example, they're all OLED. So so here you do not have backlighting, whereas LCD you do. So when it comes to power management, for LCDs, what is done is that you control the backlight. Now it used to be that there would be a single backlight, and you can turn it off or on, but that's pretty much it. Or you can change its brightness level depending upon the ambient lighting. So you would do the backlighting control. With OLEDs, brightness matters, and moreover the specific colors matter. Okay, so the power management took a more complicated, became a more richer sort of possibilities when it comes to OLEDs. So driven by the fact that displays are so dominant, again in recent years, some research groups, particularly a group down at Rice and also a group in Korea, these guys have paid a lot of attention on modeling displays, because and what can we do about it, what software controls that could be there. So in particular, because of rise of OLEDs, a lot of attention paid there. So very roughly speaking, you can say power consumption of OLEDs depend upon power by the R pixels, the G pixels, and the blue pixels, RGB. And then there is probably some sort of a constant term, and then you sum it, and the pixel per pixel sum it over all the pixels. So it turns out that some very simple low order polynomials work rather well to model the power consumption functions f, h, and k. So essentially what happens is people start with some sort of a physics driven intuition, propose a model, a parametric model like this, and then they try to fit it to the data that is observed and see how well it works. You have essentially a parameter estimation problem, use MATLAB or stuff like that. So the key thing that they try to drive towards is, given an image or given a screen, proposed GUI screen, could we estimate how much power consumption will take? Given, let's say, a sequence of images that a game has to display, could we talk about how much power consumption would have? So creating these kind of power models and then applying them at runtime in some manner. So a lot of work in this direction. I'm going to skip a little bit out here. The thing that I wanted to point out is that doing this efficiently at runtime. So kind of the idea is that at runtime, could I begin to provide software some insight into the choices of color palette it might pick and all that it would have. It turns out that specific color themes and all can have a big difference. So you can select colors and all so that things are much more power efficient. And you could play with some of the eye properties. In the sense, I want some brightness, and it turns out that our eyes are more sensitive to some colors than others. So you arrange the colors in your image so that perceptually we get an effect of brightness, which is more power, which is achieved in a more power efficient fashion than otherwise. So fair bit of work which has kind of gone into these kind of things, and they basically showed that for OLEDs it matter a lot, simply because they are emissive technologies. Another kind of display that has become very common lately in many devices are the so-called screencast technologies or network displays. So you've probably seen these things where either using Apple TV or Google's Chrome Stick or Amazon's little Fire Stick, you basically open up your laptop or smartphone and you kind of display stuff over a wireless network. There are some proprietary technologies like Google's and Apple's, and then there is also a standard called Miracast, which is from Wi-Fi Alliance. Now this one gives us a display, but display with a network component. So rules change a little bit out here because in essence now not only do I have a display, but I'm as far as the device is concerned, it's actually paying in terms of the radio, the network. So the power consumption story here becomes one more of radio, which is perhaps the other component which takes a lot in these tiny devices. So what this is showing is, for a bunch of different kind of applications, what is a dominating power consumption thing as seen by the mobile, because the display is now remote, so it's the mobile side that matters. And what you see are various components out here, but the main thing is that there is the network component, which is up there, and then there is the codec, which is the encoding the image that you have to do. You compress it before you send it out. So when you look at these kind of displays, these network displays, it turns out that the two components which dominate are the network, basically the radio, and the video codec, which can be extremely expensive, extremely power hungry. So you model both of these. In case of the network, you model it in terms of, again, static and dynamic component, one which is rate dependent and one which is not. So static is simply my radio is powered up, and dynamic is that I'm actually sending data at a certain rate over a certain time. Codec depends upon the size of the image and all, and sort of adding those things up. So the takeaway again from this is that these kind of simple first order models people develop to get kind of a good handle on what is happening, so that you can estimate and then use that estimate either to optimize your program and development time, or use that estimate as a runtime vehicle to control things out. Video codecs are usually supported at the hardware level in these devices because so power hungry, but even with that there is a fair bit of there is a lot of overhead that arises in these systems. Let's see. When these phones were first introduced, the display power was a subject of a lot of optimization, and in our smart watches also is the same issue. So there's a lot of techniques that these system designers use to keep the display shut off as much as possible. So what we saw is that there's a quality power trade-off. I can play with color, I can play with frame rate, I can play with image size, those kind of things. But then there is also a shutdown kind of things that happen. You all have phones, many of you probably have smart watches and all. What kind of techniques have you seen to manage the on-off state of the display? Or just generally power of the displays, power consumption of displays.
To me, in terms of like, so for example, on my phone, when I go below a certain battery threshold, it switches to this low power mode where the screen is, there's no activity within like maybe 30 to 45 seconds or something like that. The screen is dim, and it's just locked.
Okay, so that's a great example, and I think in recent iterations they have gone even further. I think on Samsung phones it actually switches to monochrome mode when it's in that low power mode. Okay, so that's another thing which is being done. So these low power modes, when the battery level is very low, we lower the quality of the display. What else?
When you are on a phone or on a call, it automatically displays.
Okay, and how does it do that?
Some proximity sensor.
Yeah, so proximity sensor. In fact, that was there on the very first iPhone. In fact, the original purpose of light sensor and accelerometer on the phone had nothing to do with what they are used dominantly now. It had nothing to do with fitness and activity and all. It was purely for managing the display. So the act of picking the phone up and bringing it close to your cheek, okay, so they basically kind of were optimizing for that. And that technique has been around, has stayed around because it's very powerful. Your watches have that, like you lift it up and then it turns on, okay, so that action is there in most watches. So that's another dimension for activating the display. Yeah.
Screen brightness.
Screen's brightness. So how is that controlled? Huh? Light sensor, ambient light. So the difference between the ambient light and the screen brightness. So that's the control which they all have. So and also, I guess there are other things which are happening around displays. Like one of the things that emerged on iPhones over the past year or so was this whole thing that automatically at night it switches to a more yellow, less blue kind of thing. So they kind of that's more about comfort than power, but just wanted to bring that out too. Yeah.
There's also the always-on display these days that's coming into most Samsung phones.
Correct, so they are for at a glance kind of thing and all, right? They're monochrome. Am I right or no?
So on mine, I think it's color.
It's color. Do you know what technology are they using? How do they?
I have a feeling what it is it's an OLED. They try and optimize it on change, so
Okay.
activating the pixel doesn't take that much energy.
Okay.
Sorry, it takes a lot of energy to activate it, but once it's activated, it takes almost no energy to maintain its.
Is it a separate display or is it?
So if I just turn it on here and you just put it on its side, it just shows up right
Okay. There's another thing which the really low power display are the so-called e-ink, which were used in Kindles, which Kindle uses, and they are really low power because once you write it, it's a persistent display. Okay, so except that they're not very dynamic in the sense that rewriting is slow and all. So that's another one. Another thing which is done is, which for example some of the laptops, like my laptop has it, which is they have two GPUs. One is a low power one is a high power one, and depending upon what kind of applications I'm running, it silently kind of switches back and forth between the two. So like if I were to run a game or play something, it switches to that faster GPU. Yeah.
I think there's a new feature in iOS 10 which if you hold your phone like this and you rotate
Yeah, so I've also noticed that there is something about upside down also that they have introduced. So they're playing with a lot of these things. I also understand that some Samsung phones, based upon your face recognition, activate the display or something like that, like in the sense that am I actually looking at it? So, like for example, with my watch, I have noticed what happens is if I'm driving, then sometimes when the steering wheel motion appears equivalent to as if I'm lifting to see the watch, and therefore it turns on, and it's totally wasted energy during those periods. Um, so a lot of optimization has gone towards display. So this display, we see the radio. We'll have a whole lecture on radio later on. What other there's GPS, which is actually a huge power consumer. Um, I'm not talking about this GPS and this thing, but GPS duty cycling, not giving you direct control over GPS, making use of other signals like Wi-Fi and cellular to minimize activation of GPS, making use of accelerometer and all to see whether you are actually moving, so that you don't keep doing redundant GPS stuff. So radio related and display related stuff is pretty commonly being optimized. More generally, for what are called as post PC devices and Internet of Things and all, it's all this other stuff which has beginning to play a much more important role when it comes to sort of power consumption. Now, in many cases, also by the way, we don't even have displays. So you have other type of human-computer interaction modalities like whatever speech recognition and those kind of things. Little stuff like, for example, our phones and these things now have this voice typation, Siri and Alexa and these kind of things, right? So just that simple thing, hey Siri. Well, there has to be at all times something listening for it. So the first generation was the Hey Siri feature was active only when your phone is plugged in. Then I guess Motorola and Samsung when they started introducing word spotting while the phone is still just purely on battery, and then now iPhones also have it. So behind the scene, what happened is a lot of optimization on this thing. It was continually listening for an acoustic signal, identifying that particular word can be extremely. So while a nice feature can be extremely impactful on the battery, there were a lot of work and all sort of optimizing this. And the same thing for face recognition or these other kind of strategies. And they are often combined with some sort of thing about is the phone being activated. So like, for example, if there is a facial recognition thing, it's probably reasonable to think that there would be a picking up motion before I would look at that. So you can use that to activate it. So some combination of using sensors to activate stuff. A lot of sensors that you might think are, can be, do not consume power themselves, they may be very power hungry. So like take accelerometer, if you run them at a high rate, they themselves can consume a lot of power. Gyros, which are part of these things, are order of magnitude more power hungry than accelerometers. So accelerometers you can operate at microwatts. Gyros, which are part of the same IMUs, are milliwatts. So big difference, 2 to 3 order of magnitude. So you have to be very careful about these things also. Also, there will be some processor which will need to process that data. If it is your main processor, then all this activation is coming at the cost of keeping some main processor up all the time, not sustainable. So other change which happened in recent time is that they have these specialized processor just for word spotting or sensor processing, which are running all the time. They are kind of tiny microcontrollers, vigilant all the time, and running kind of just behind the scenes. So if you can bring that power level down to microwatt type thing, then you can do it all certain always on things. So main change that's happening, or I guess a difficulty that happens is a lot of power management techniques depend upon knowing the context, knowing the user context. But they themselves need to be on all the time. And therefore, power management itself requires careful design of some very low power implementation that nevertheless has certain level of smartness behind it, so that you can do all this cool activation type methods and all. And that's been a tension. Similar numbers that I got for um, Apple's sort of devices as opposed to laptops and computers. One thing that you would see is that look at power supply efficiency. It goes significantly down. For bigger computers, it was 90s, and this is for iPhone 75%. Okay, and this so power supply efficiency and all kind of underlying smartness behind it. There's a lot of innovation happening in this regime. Also, part of the thing is also you want to minimize the no load footprint. I wanted to go back and show you one thing. Yeah, here. See, for example, the iMac off 0.24 watt. This is entirely your power brick. Okay, so this is a so-called vampire energy usage, which happens and added over billions of devices that exist. That this can be quite significant also. People have done studies of other kind of devices which have been emerging. So Google Glass, I had a student presented last time that I offered this class. So Google Glass internally is like a essentially like a smartphone. It just has a different kind of display and stuff like that. It has a Wi-Fi radio, obviously. So so we are seeing emergence of a lot of these devices which are putting mobile phone type functionality in kind of different form factors. If you look at the Android Wear watches, they actually are pretty much like smartphones. They run the same operating system, similar processors, stuff like that. So, you see, I mean, at some level, not very surprisingly, their behavior and the models and all that work for smartphones work pretty reasonably well for these as well. One other thing I wanted to mention was that one very common strategy that people do when they do these kind of analysis is that they put some sort of a special circuit in between the battery and the rest of the phone. Now that works great for phones which have replaceable batteries. So several groups have done that kind of stuff. So the idea is you can, if you're doing it on whatever your lab bench and all, you certainly can. You remove the battery and then kind of interpose something. But people have even made special back cases and all, where you can then have something which looks like a fairly portable phone, and you can kind of go around and all and collect data. So these kind of data collection exercises and all, sort of people have done and invested stuff. It's unfortunately not possible with phones with sealed batteries, but a lot of at least phones until fairly recently used to have replaceable batteries. As expected, so in Google Glasses, the display is a heads-up display. So there's a little kind of projector, and you kind of begin to see the display being done, hovering in front of you. So again, they have done modeling of that. So the display power is very dominant. Scales with brightness, scales with the content, so the colors, for example. A fair amount of static power consumption happens, so just to keep kind of the system up and running. And in this particular case, sort of since the image is being projected, so there are other effects which kind of begin to come into play. But just as a perspective, iPhone 4, the paper was in 2014, consumes the display consumes 420 milliwatt. Google Glass, which was again around that time, in its fullest bright mode is 674 plus 196, almost twice the display power of the phone device. Okay, so all this heads-up display and all is coming at a cost of a higher power consumption kind of thing. These guys also analyzed other things. So like Google Glass has a bone conduction speaker, and other type of speakers have also emerged. I think just over the past 12 months, we have seen emergence of in-the-ear wireless stuff like the Apple, what is called earphone or AirPod. Braggy has these things which are little computers that go inside your ear and they talk through your skull using magnetic induction. So all sort of interesting new devices are beginning to emerge, and so there's a fair bit of analysis on their sort of impact as well. And then of course you have Bluetooth and stuff like that.
Earlier you mentioned numbers for the power efficiency for adapters that go to the wall. Is there any similar analysis yet for like wireless charging or anything along those lines?
No, and this might so yes and no. So some years ago, so wireless power supply is actually a very old technology, all the way back to Nikola Tesla. His whole fame was because of that. So it has been coming off and on, off and on. Okay. A few years ago in this course, I had a group as a project do that kind of analysis for a product which was kind of a gigantic antenna kind of structure, and it would supply power to little sensor nodes in a room type deployment. So those guys did do a lot of analysis on energy efficiency in that kind of setting. Specifically for, I guess, what you are referring to, namely wireless charging of my phones and all, I have not seen. And in fact, I mean, my guess is intuition is, yep, there should be a lot worse. And you might ask also things like, given that we have billions of phones and all, are we kind of actually worse off from the energy footprint perspective on the phone if their efficiency goes? So that would be interesting. Another innovation, so to say, which is happening on the power adapter side is the rapid charging. Those of you who have newer Android devices, Qualcomm-based ones, you would have probably seen this thing that they have this. When you plug it in, they often say rapidly charging. Okay, and that's because they essentially charge the battery in a very high current mode. The question then becomes that these different ways of charging the battery, what kind of impact do they have on the efficiency? Okay, that is, am I gaining in speed at the cost of the efficiency there? So there are still, I think, some interesting questions that are perhaps worthy of a project idea. Yeah.
So I was taking Leaky's class about a year ago, and he also touched briefly on like the different types of charging.
Whose class?
Lazy.
Okay.
And one of the things that he touched on was that when you use fast charging mode and stuff, it is really bad for the battery. Is that still true, or?
Yes. Yes, it is. But again, I guess the thing is you're leveraging the fact that meanwhile batteries are also improving. So I can take that improvement which was coming from the battery and use it to give you this feature of rapid charging. Okay, you could have used that headroom in a different manner, namely your battery will last longer. But I guess the mindset is that as long as your phone lasts for 2-3 years, you're happy. So any further gain in battery technology, we're going to use towards these kind of features. But I haven't seen anything published on Qualcomm's fast charge or rapid charge or whatever they call it and all. A little bit of it is hush-hush because it's not like it's a separate product. You have to use their processor to kind of get that whole thing. But some sort of a study of that, its efficiency, its characteristics and all would be kind of interesting. And then wireless charging certainly is getting a lot of lots of products. And in different spaces, there is a company called Vitricity, or an MIT startup. Their game is kind of different. They actually seek to do wireless charging over a couple of meters kind of thing. So wireless charging, there's a whole bunch of different stuff. Okay, so there is one which is like your electric toothbrush type stuff, very close contact. Phones are like that also. You actually are sitting on top of charger with literally millimeter type separation. Those of you who were in Professor Markovic's seminar week before last week, you might recall that he talked briefly about that how current chargers require very careful alignment and all, and that how some of the work out of this group has basically done things where the two parts, the charger, like your the coil which is inside the charger and your device, like your phone, it could be some distance away or it could be laterally shifted and still be okay, because his application was supplying power through the skull to the embedded device, and the point is that things can move around. Another context where I have seen an even more extreme power delivery kind of thing is for implants in the eye, retinal implants, basically. So supplying power from them. So you kind of wear a type of a glass, and then you have a camera mounted there, and you have some sort of a power supply mechanism, wireless, which is delivering things. So wireless power delivery is kind of an interesting hot topic commercially. Right now, what you are seeing is that, like Samsung's devices, they sell this kind of a little station of sort, and you put your phone on it. So, or at Starbucks, you might have seen those IQ chargers or whatever they're called. Okay, so they're embedded in the table, and you put your phone on top of that. So they are very close, but there are technologies which seek to do it through the air over some distance, and then there are technologies which are using magnetic resonance to do transfer over a couple of meters. So my laptop may be sitting here, and there's something on the ceiling, and it's getting power from it. So yes, there will be loss, obviously, and the farther away you are. But it's a technology which I think the convenience of that argues in favor. Convenience, and the other thing is if they can deliver, if wireless power supply can become really efficient, and we have wireless headphones and things, then your phone can be entirely enclosed and therefore can be even more water resistant and dust resistant, and also these things all kind of play together. So there are other implications of some of these things as well, which are driving things. Okay, let's see. So Google Glass overall, these were kind of numbers. Idle mode, 22 milliwatt. Wake up mode. So while it is waking up, it consumes additional power, and this is something that you would see in lots of systems. That when you put them to sleep, and then when you are waking up, during that short time when it is waking up, it actually may consume even more power than in the active mode, and that's a penalty you have to account for. So in some senses, again, you can think of systems and subsystems as having these energy or power states, and then when you're transitioning between them, there is a time that it takes and there is an energy it takes, and therefore your decision to shut down has to account for this cost of saving state and going to shut down, and cost of reviving the system, coming back on. Processing 300 milliwatts. So these are actually numbers which are very comparable to what your phone might see, or even higher in some cases because of the poorer display. But the flip, but on the negative side, I mean, you're much more limited in terms of battery size and all. Yeah.
Was this done on the old Google Glass that got discontinued, or the new one?
There is no new one as far as I know. Yeah, Google discontinued it. Exactly. I guess, I mean, there were a lot of other issues behind this, but these things will take some time, and maybe this might not be the best form factor. I think now I'm also, so there are two other form factors that I have seen for such devices. Of course, the watch type stuff is the ring. That has emerged an interesting possibility because people wear ring, and if you can have some stuff embedded there, it's also on your finger, so some of the medical stuff can be done as well. And the other one is in the ear, which I'm less sure about because I have one of those products from this company called Braggy. It's pretty cool. It's so two devices entirely wireless. It's a gesture-based and voice-based interface, so I can touch it to control stuff, and then it says stuff. So the setup was one of the coolest one. I bought it, plugged into my ear, and then it guided me through verbally the setup. Okay, I've never seen that in a device. It has 8 gigabytes of RAM or whatever memory in that device, 23 sensors. It measures my pulse rate and motion and everything, all in that tiny little kind of device. And it talks to my phone over Bluetooth, and the two talk to each other through the magnetic communication that I was talking about. Okay, it turns out that wireless doesn't work standard RF wireless doesn't work very well because our brains are kind of, again, a very lossy pathway. So these kind of devices are offering some interesting things, but its battery life is awful. It's marketed as that you could have all this monitoring and all while you are exercising and things like that, but I barely get a 2 hour battery life, maybe if I'm lucky 3 hour, not even sufficient for a long weekend hike, okay, so let alone, so you can kind of do it for small exercise stints in the gym, and then again you have to recharge, so long ways to go there. Okay. Yeah, these are some other numbers like the Google Glass doing stuff, navigation, stuff like that, and of course the power numbers kind of go up, and correspondingly kind of the battery life goes down significantly. Internet browsing and all. So these there are long ways to go. So I think the combination of battery life issues and all are still there. Telephony, for example, 1300 milliwatts. So these are significant numbers. So I guess one of the insights, one of the things in the paper was that your standard Bluetooth headset and all are much better than if you're using Google Glass to do the telephony thing, because it has a lot of other stuff which is active. If you look at now these virtual reality type stuff, and also there was I was talking with a faculty candidate, and his work was on making these VR headsets wireless, tetherless. Okay, so you could imagine. I think one of the things that people are striving towards is this augmented reality or virtual reality married with the real world and all. And in that case, you want these things to be out there. So you can imagine a version of Google Glass which begins to overlay information, projected displays, and things like that. The problem with these things is also currently, if you look at the VR stuff, it operates at a much higher frame rate, 90 to 120 frames per second or more. It has a heavy suite of sensors for tracking your head and stuff like that. And the resolution is very high. So this guy was telling me that the work that he had was the radio link between the glass and the PC is 7 gigabit per second. So it's not your Bluetooth. It is very different link. It's not even your Wi-Fi. Fastest Wi-Fi right now is around a gigabit per second. So these guys are using what are called as millimeter wave radios, okay, and kind of achieving that. So I think as we see these different device options come into play, we see this constant shifting of the thing. Like as these millimeter wave radios make into portable devices, they'll probably become the big power consumer because they are power hungry, or at least the first generation devices. So some more numbers, but point basically was that a lot of things that you would like to do out here with these devices are very power hungry, like running a face detection app, 100% CPU utilization, more than 3 watts of power. I always thought that a cool app on my Google Glass would be that when I meet you years later and I don't recognize you, at least it pops up your name so that I'm not embarrassed. Those kind of things. But I think as you can see, that's long ways to go. 3 watt for running this kind of stuff, not with the batteries possible. So standard answers to these things include custom chips. So instead of running software on a processor, let's make a custom chip out of it. Unfortunately, it works fine for structured signal processing, mathematical operations and all, where you can kind of scale things and all. A lot of work, like for example, the Markovic's group and all. But it does not work well for the more amorphous, control-heavy kind of software and all. So, and a lot of these things are of that nature. A lot of higher layers of artificial intelligence is not your signal processing kind of stuff. It is much more unstructured graph algorithms, and also their sort of things begin to break down. So I think lots of opportunities and all this kind of remains an issue. Another issue, another driver for for making some of these things lower power also comes from the risk of thermal damage to the tissue. So it's one thing that my phone consumes a lot of power, and occasionally I consume that how hot it is getting. But it's a very different issue when the device inside your eye or inside the brain begins to heat up and then causes cellular damage nearby. So in those applications, there is added sort of issue which comes up. So these were some, again, the same group had done. So every watt drawn by the processor, OMAP is a TI processor. The surface temperature rises by 10 degrees Celsius, and so the glass surface temperature will rise by 90% of that in 10 minutes because there is a thermal impedance which slows things down. Blood vessel damage can occur with continuous contact to surfaces in this particular range. So skin damage and cellular damage, and also that. So as we get into these domains which are much more personal, and devices that you are wearing or devices even inside our bodies, these things become more important consideration. So I guess the main takeaway from this part of the presentation is that displays are an issue, and we are seeing all these, and I would say more broadly, the way humans interact with these devices, because we are seeing emergence of all sort of interesting modalities, but certainly new forms of displays, but other oral and gestural kind of interfaces as well. And as these devices are coming closer to our bodies, the thermal issues also begin to dominate. But there's a lot of creative stuff happening in this space. Okay, so over time one of the direction it seems that a lot of these devices will take is that they will not have any built-in display. They will just project into a nearby surface. And the other one is if our world has lots of these wireless displays and we just kind of just talk to them. So what directions emerge would be kind of interesting to see. Want to spend a few slides talking about radios a little bit. So they already came up. And more broadly communication interfaces, but radios specifically, because in energy challenged systems they are the mode of choice. So if you look inside any communication system or any wireless communication system, what we have is, like, we think of it out, there is an antenna and bits going in, radio signals going in, radio signals coming out. But in between there is kind of a chain of electronics and then layers of software which kind of make all this stuff work out. So out there we have the operating system with its network stack. At some level it passes a packet to the radio interface. Inside there, after some queues and all, and some sort of a channel access protocol, we go through this process of encoding the digital signals. So this is the so-called modulation, converting it into analog, amplifying it, sending it out. On the reverse side, we get a very weak signal because it has traversed through the air. So we amplify it, we digitize it, we go through the reverse process of demodulation, decoding, and then again hand it over to the protocol state machine, and then finally again back to other higher layers of the protocol stack. So that's how it looks like. Now, question then becomes, how could we, what's a reasonable model for abstracting this away? Just like we did it for the processor, could we gain a similar insight out here as well? So very crudely, you can think of a communication system as really having a receiver and a transmitter, and there is some sort of a channel in between, air, or whatever, this wireless in this particular case. And you can think of these systems really having three main sources of energy consumption or power consumption. So all that software and digital coding and analog stuff that's happening, we can think of it as some sort of a transmit electronics. I'm lumping software into here also because software itself doesn't consume power, it's because it's running on a processor. So it's all lumped out here. It's the transmit side electronics. And likewise, there is a receive side electronics. Okay, it's doing all the decoding, demodulation, and stuff like that. And then there is this amplifier whose job is to take the bits and send out radio waves at a high enough power so that they arrive at the receive antenna with adequate signal strength so that I have a successful communication. If it's not wired, it's wired. If it's wired, still same story holds true. You will have some sort of an amplifier amplifies the signal, things go over a coaxial cable or some other cable and arrive at the receive side. So these are three very broad categories. Now, it stands to reason from this that if my transmitter and receiver are far apart, then to achieve the same data rate or same error rate, I would need to transmit at a much higher power out here because my signal will decay over a longer distance. So therefore, it stands to reason that for for long distance stuff like cellular radios or satellite links or stuff like that, this ERF will dominate, and electronics will be reasonably minuscule. So whatever is this guy's power feature is going to dominate. What do you think would be a good first order model for ERF? These are electromagnetic waves traversing through a channel. Huh? Not, yeah, so, but what would it be? Go back to your physics. How does the power of square if it's vacuum and there's nothing else? But of course, it's not. They're clutter and all. So realistically, in cluttered environment and all, you'll probably see d to the power 3, 4, 5, something like that, some higher power. So a very good first order model tends to be is some sort of a d to the power k plus some other terms and all also. But that's a reasonable kind of a model that you go with. So your cell phones talking to cellular radio, this term is probably going to dominate because your cell station is probably a mile or two away. On the other hand, your cell phone talking to your smartwatch, not even a foot away, that's unlikely to dominate. Okay, so depends upon which term you're talking about. Then we have these two electronic terms, and for electronics we did not talk about analog, but for digital part we already saw the models that work with processors. So same kind of thing will work. There's frequency, voltage, stuff like that. Which one do you think will be more hungry, receive or transmit? Receiver, transmitter, receiver, transmitter. Those who are saying, let's say, receiver, why do you think so?
Some cost.
Huh?
Most of the cost as the receiver takes more energy.
Okay.
It's because probably the receiver is speed sampling. Even there's nowadays the receiver is speed sampling.
Okay, that's a good point. And so one thing is if a poorly designed receiver is always listening. Okay, whereas a transmitter has advantage, it can only turn on when it is transmitting, right? Good point. But let's imagine automatically we have a protocol so that we know when we are going to talk to each other. So receiver wakes up at the same time.
Could it have something to do with trying to synchronize the incoming signal with the local clock?
No. But think of what is a receiver doing and what's a transmitter doing. Transmitter is just coding. So it has a signal and it encodes it. Receiver has a much harder task because when it gets the signal, it has been corrupted by noise. So now it has to do this search algorithm to identify that in the presence of all these noise and all, what was the most likely thing which was transmitted. So it has a search optimization algorithm. Those of you who have done any communication class, you have probably seen some receiver architectures and all. Much algorithmically a lot more complicated task. So just generally speaking, intuition would suggest that receivers would be, for a lot of scenarios, receivers are going to be a lot more complicated algorithmically than transmitters would. So coding is easier, coding of this type modulation and all is easier than decoding. On the other hand, if you are coding for compression, then coding is more intense than decoding, because when I'm trying to find out compressed things with the smallest size, so JPEG encoding is more intense than decoding, for example. So you see the structure out here. For long separation, like cellular radio, the green component, which is the RF, dominates, and the other two are tiny. On the other hand, if you are looking at short range links, the electronic components dominate and the radio component is very tiny. In fact, in the extreme cases, you would find that the receive electronics is more than the sum of RF and transmit electronics. Okay, that is, the cost of sending a bit is cheaper than energy cost of receiving a bit, and that changes a lot of assumptions that you can get away with in the other regime. If nothing else, if you are doing a COM theory type class and all, they never talk about the receive energy. It's always, when they talk about energy per bit and stuff like that, the focus is on the transmit side, because kind of the implicit mindset is it's the RF component which kind of dominates. But as you can see that across the different range of things, in different regimes, different things will matter. And you would see that if you attempt to buy like a Bluetooth LE kind of radio receiver or Zigbee and all, you would easily hit for the extreme low power end. You will easily get into a situation where your receiver is more power hungry than your transmitter. And it changes how you approach communication in multiple ways. So one of them is the point that he was making at the back, which is my strategy of staying up, waiting to listen, is probably a really bad idea now, right? Because if I was dominated by the green stuff, green plus the cyan, then I have to be careful about transmitting, but receiving didn't really matter. So a lot of the network protocols for channel access and all were designed like that. The receiver would just stay up all the time. But if I'm in a regime where receive dominates, then I have to be very careful about when I am receiving. In fact, I can afford to perhaps be profligate about transmitting if I save on the receiving side. So you might recall from those of you who wanted to go to A, when I talked about time sync, one of the ways we sort of address that is by carefully synchronizing kind of transmitters and receivers. But part of the reason we do that is for this thing, that receive can dominate. So radio energy, I should title it not quite state of the art anymore, because the slide is a couple of years old. But nevertheless, you see for different radios, cellular, Wi-Fi, Zigbee, Bluetooth, and you kind of see different kind of numbers out there and all. But generally speaking, you see, like for example, for cellular, receive is 350 milliwatt, transmit is 1.5 milliwatt, 1.5 watt. Okay. So and number to keep in mind is nanojoules per bit. It's roughly 10,000 or so. Okay. So I'm essentially spending 10 microjoules per bit that I am sending out. By the time I hit Bluetooth, you see several things. So firstly, absolute values have gone down considerably on the transmit side, because ERF term largely disappears. But my range is so much shorter, even though my data rate is high, megabit per second versus 200 kilobit per second. The other thing is that you would see that receive and transmit have come a lot closer. And in some examples, like this one, Zigbee, receiver is more expensive than the receiver, consumes more power than the transmit. So depends upon kind of specific radios and all, but the broader point is you're really very close, if not receive dominated. And the other thing, therefore, what happens is that energy per bit sort of goes down quite significantly. One other number I've sort of not shown out here, maybe I have some slide. If you compare it with energy per instruction of a processor, you would see that communicating a bit, even with Bluetooth and Zigbee, is order of magnitudes more expensive than executing an instruction. And that's something which is often cited as a reason to process before sending. So you are, I think if I recall right, that ratio between energy cost of executing an instruction and energy cost of communicating a bit, that ratio is communicating is anywhere from 100 to 10,000 or more times more expensive. So what that means is, if by doing a bunch of instructions I can avoid sending a bit, I'm better off. But these things also change. There is a new type of radios which have emerged, and in fact, again, its energy implications or even a project around it might be interesting. Are radios which do not generate where ERF is 0. And the way you make ERF 0 is that you don't use a local source of power. Rather, you make use of some signal that someone else is sending to you. So these are so-called backscatter radios, and kind of the idea is that the receiver or some high power source like your Wi-Fi base station or something is sending a signal to you, just a sign, just an RF radio wave carrier. And instead of having an amplifier out here, all you have is a little circuit which changes the impedance of the antenna. In effect, makes the antenna act like a mirror which you are rotating. So this goes to this classical way of signaling that mankind has used often, which is a piece of mirror. I'm wishing to communicate with you, sun is shining, and I'm going to signal you by rotating the mirror. So the signal which is going from me to you is actually the sunlight, which is available for free. The energy I'm spending is the energy to rotate the mirror. And you can, which is another way of saying it, I'm changing its reflectivity, right? I'm reflecting or not reflecting. And with antennas, you can do that by changing the impedance in the antenna. So I can make the antenna bounce back a signal or not bounce back a signal, but the signal itself is coming from someone else. And then there is an additional thing, I have to somehow make my information rise on that. So again, do it by modulating the antenna. Long story short, these newer radios which are emerging, they make ERF go down to 0. So again, we are back to a regime where transmit becomes much cheaper, because if ERF disappears and transmit electronics is low, so essentially you have a free radio in those cases, free. So we put together all these insights and all. So now if you look at a complete wireless system, you can begin to model the electronics part, the amplifier part, and the electronics part on the receive side. Your electronics, the signal processing and all follow very much like our processor-like model, so very similar. Your power amplifier, the one which was the ERF component, it usually basically has a very simple model of a constant term plus another constant term multiplying by how much power you want to send out. So very simple models work. Long story short, for a transmitter, a first order model is that energy per bit is a constant plus another constant times d to the power n. D is the distance. We talked about earlier that how free space propagation is d squared, but more likely you're going to have d to the higher power. This alpha term is kind of all your electronics and all. And this beta term relates to the power n. Okay, so this is a good first order model. For the receiver, a good first order model is simply E bit equal to gamma, because receiver has no distance dependence. This d to the power n is assuming that I'm transmitting just at the right power. If I always transmit to reach out the maximum range, then instead of d to the power n, it will be d max to the power n, in which case it will become a constant. Okay, so to use radios smartly, just like with processors, you should run at just sufficient frequency. Here you should operate the radio, the amplifier in the radio, such that it transmits a signal at just enough power. And this is called transmit power control. There are sophisticated protocols, like when your phone talks to the cellular tower, if you are close to a cellular tower, your phone will transmit at a lower power. And as you move away from the cellular tower, your phone transmits at a higher power. So in cellular system where ERF, where this term dominates, all that sophistication exists. For things like Bluetooth and all, possibly not, depends. Because the contribution is tinier anyway, so why complicate things? The protocol for doing all of that will complicate rest of the system. So, but this transmit power control is a vehicle that sort of you have. So all of this then in turn lead to some interesting things. So let's say, for example, I have to send bits over to a certain distance. If the second term dominates the distance dependent term, then I'm better off sending in multiple hops, because each hop, if I have h hops, each hop will have a distance of d over h, and therefore to the power n, so I'll have a significant reduction. If on the other hand the first term dominates, then the story is going to be different. Because I am immune to distance, so might as well send in a single hop as opposed to multiple hops, because then I'll be paying this penalty at each hop. So multi-hop transmission is a powerful tool if you want to traverse over long distances, because then over long distances this term dominates, and therefore I'm going to better off. In general, you're going to have a sweet spot, that is, there's going to be an optimal hop distance which you should send at. If your distance is more than that, do multi-hop. If your distance is less than that, do direct transmission. So for people who are worried about power and communication and all, multi-hop is a tool that you can leverage. So this characteristic distance basically says what's the optimal distance that the transmitter and receiver should be at. For less than that, single hop communication is good. More than that, you should multi-hop. And it depends upon this ratio between distance dependent term and distance independent term. Much like the argument I was making in context of leakage and dynamic processing power, which is the ratio between them kind of decided whether you should sprint or whether you should use up all the time. Final note on the radios. When just like processors, you can also shut down the radio. So same story that I had for processors, namely, should I run the processor at the highest possible speed and power it off, versus run it just at the right speed and consume all the time? Same thing applies with radios also. Am I better off running the radio at the highest speed setting? Highest speed setting will require me to transmit at a higher power, and therefore that ERF term will go up. Versus should I just scale it at the right thing? In many regimes, very much the same argument as we have for processor. You would be better off transmit as quickly as possible and shut it down. It turns out that radios are, again, just like operating system type issues and all came in the way of rapid wake up and all. Radios have the same issue. There are a lot of stuff that radios have PLLs and clocks and all. They take time to wake up. So when you put a radio to sleep and bring it back up, all that stuff come into play, and then your protocols have to resynchronize because a mobile node had disappeared and now it comes back up again. We have to know about it. So again, roughly 10, 12 years ago, a lot of attention began to be paid to radio startup time. That is, designing radios that can rapidly wake up and be active on the network. Required, again, optimization both on the hardware side as well as on the protocol side, much like what happened in processors. And standards like Zigbee and Bluetooth LE, the so-called BTLE or smart Bluetooth, are examples of that. If you look at classical Bluetooth, your Bluetooth which is used for acoustic transmissions and stuff like that, when it wakes up or when it takes a long time to sync in with others, and could be even seconds. BTLE, on the other hand, is a very different thing. It doesn't require that explicit sync in, so it is actually optimized for this very low duty cycle operation, where I want to send you a packet, go back to sleep, send you a packet, go back to sleep. Okay, so BTLE is an example of a radio optimized for this rapid wake up, ultra low duty cycle, whereas classical Bluetooth focused on rates, but at the cost of it was awful at duty cycling. And there are many other examples of radios which have been optimized in this direction. Again, attention got paid to these things only in the past sort of 10 years or so. So I'm going to stop here. We're going to continue on Monday to wrap these slides up. And I will, Nathan didn't come, so I'm assuming that I can give away his slot. And so I'll hand out 4, maybe 5 PTEs by late tonight. I will send out an email to everyone when I've allocated the PT so that you know that you're not getting one and therefore can stop coming.